LearningMeasure.tv, science and engineering podcast with emphasis on measurement. Brought to you by David Archer and LearningMeasure.com. Episode 12, Ohm's Law.
Hello, I'm David Archer, owner of LearningMeasure.com and LearningMeasure.tv. This podcast is sponsored by TradePub.com, GoToMeeting.com, and is part of the Blueberry community of podcasts. A whole bunch of podcasts out there at Blueberry. You might want to check them out. Anyway, first part of our thing, I want to always say a little bit about LearningMeasure.com. LearningMeasure.com is a subscription-based training service. You get 2 weeks free, and then it's $5 a month after that. The $5 a month is to help us produce more courses, this podcast, among other things, and that's what that's about. I've been getting a lot of questions lately about how much my courses cost. Well, the courses are free. The only cost is the subscription. So once you subscribe, you can take any number of the courses that are online. We just want a little bit to pay for our expenses for doing this. Also, employers out there, if you want to sign up as an employer on the site, first of all, you'll have the ability to see progress on what your employees are doing with courses on our site if those courses were needed. Plus, we have the ability to have company-specific courses made if required. This week, the topic is Ohm's Law. This week's topic is Ohm's Law. And that's because, basically, of a question that one of you asked. So, Ohm's Law is credited with George Simon Ohm, this guy here. He was born in 1787 and died in 1854. He's credited with, well, he did research in electricity and actually acoustics. But he discovered things such as, for a resistor, the resistance is proportional to the length and inversely proportional to the cross-sectional area. But he's more famous for his law, Ohm's Law, which we now call Ohm's Law, is that E, which stood for electromagnetic force or voltage, E equals IR. Voltage is current times resistance. That's, in particularly, they're talking about voltage across a resistor, what the current flow through is through that resistor. Well, what are these things? Well, that's kind of what we're going to talk about in here. Okay. The first thing we want to talk about is analogies. In a lot of times, electronic circuits are talked about in analogy with water. For instance, this is the symbol for a battery. It produces a voltage, what's called a voltage. Let's say this is a pump. It produces something called pressure. This is something like a force per unit area. This is a work per coulomb, or work per unit charge, but that's another story. I'll get to that in a minute. But it's analogous to pressure. Pump is what drives water around a water plumbing system. Voltage is what drives current around an electrical system. Well, current here is something per unit time. Like if you wanted to measure the flow rate here, we'll call it F for flow rate. Its units are something like liters per second, let's say. So going past a certain part in a plumbing system. Well, if you had some sort of, and then you have pressure here, P, And you might have some sort of resistance in something analogous to resistance in the water circuit. Okay. Let's say you have a big fat pipe filled with sand. Let's say there's sand in here. Okay. This is going to restrict the flow. Now this is a higher pressure region here, and it's a minus pressure region here. So the water flows from higher pressure to lower pressure. Same thing in electric current. Let's say a point here, you measure current. Okay. Well, that's measured in what's called coulombs, which is what you measure charge in, per second. Okay, so here you got liters per second, here you got coulombs per second. And it goes through something like a resistor. That's a symbol for a resistor, R. Well, you could also define something we could call this R water or something. That's R there. Well, what Ohm's law basically says, this resistance here, of course, is defined as the voltage E for electromotive force divided by the current, which this is in volts and this is in coulombs per second. And a volt is a joule per coulomb. So this whole thing ends up, well, we can talk about that later. Well, this is given a name ohm, also called ohms. Okay. Ohms is a volt per amp. Current is measured in amps, which is a coulomb per second. Well, you could do the same thing for the water circuit. You could define the resistance to the water flow as the pressure divided by the flow, and this would be in something like liters per second per whatever or meter or force per unit area divided by liters per second. I don't know what kind of unit's that. It doesn't have a name, but we give this also this unit of this quantity as ohms, also to honor George Simon Ohm, who came up with the idea of resistance. Now, Ohm's law is more than that. I mean, you can only go so far with analogies, as we'll see in a minute. So the water and electric circuits, well, there's often analogies made between them. And we're going to show at least one case where they aren't analogous. But before we get too much farther, okay, Ohm's law as we see it here, E equals IR. Okay, for those of you who remember your algebra and the equation of a line, y equals mx plus b. Well, here x is the current, y is the voltage, r must be the slope, intercept must be 0. So if you were to graph voltage as a function of current, you'd get a straight line whose slope, if that's the only parameters that are there, you get a straight line. Okay. Some bodies that are in electric circuits follow Ohm's law, not all of them. For instance, in fact, modern electronics relies on this not being true. For instance, the curve of a diode might look something like this. Okay. So the voltage and current are related in some weird way, and you depend on that. Now, reality, even resistors don't follow this simple rule because there's other things in here, and we'll see that. But it's approximately true for a lot of circuit elements. In fact, even if Ohm's law were not true, you still could define resistance as the ratio of a voltage to a current. Okay. Before we go too much farther, got to do our little ad here. Got to actually pay some bills. Okay. Go to meeting. Do more, travel less. You could say, if you say, I waste hours in traffic to get my clients' offices for meetings. In fact, I spend more time getting to meetings than actually do meeting. This can't really be productive. Great news for anyone who feels unproductive. There is an easier and more affordable way. Go to meeting. The award-winning service lets you hold meetings over the internet with people in multiple locations. Just log on to gotomeeting.com and start meetings with a click. Instantly, everyone sees your computer desktop on their computer screen. It's like the meeting in person, but less expensive and less time-consuming. Hold limited meetings for one flat rate. Meet from your office, home, hotel room, anywhere, anytime. To try GoToMeeting free for 45 days. Just go to gotomeeting.com/podcast. That's gotomeeting.com/podcast. Do more, travel less with GoToMeeting. Okay. Now, some of the things that aren't true, that aren't good analogies with electric circuits. In fact, the SI unit, one of the SI base units is current. And the unit is the ampere, which is a coulomb per second. Coulomb's a measure of charge. Well, this is what's defined. This is actually what's derived. And the reason why is if you take two wires and you have a current going through them, it produces something called a magnetic field around the wire. You've seen this within like electromagnets before, probably lifting up things like cars or paper clips, or whatever. That when you have current going through two wires that are parallel, there's a force between them. And if the force on one of the wires is the other way, it's an attractive force. Well, anyway, the SI unit of current is defined as the current that you have a certain force per a current that provides a certain force per unit area, or force per unit length for two parallel wires, a meter apart. And that's often measured in something, it can be realized with something called a current balance. Okay, so that's elementary charges are then, once you've defined current, the elementary unit coulomb is you run a current for a second, and that will tell you how much 1 coulomb is, once you've defined an ampere. And the ampere basically is defined in terms of the meter, the kilogram, and the second, because there's the forces involved. Okay, now that's what a current. Well, what's a voltage? Well, as we talked about a little bit in the last podcast, if I have something like this eraser and I move it from here to here, I have to put force on it. And the force times the distance I move it is called the work I do on this object here. Well, voltage, if you have some charge here, say Q, and you move it from here to here, let's make it more of a straight line so it's easier. Let's say you move the charge from here to here in some sort of field. So you move it from here to here. Well, you have to apply some force to move this charge. And so you do work on it. So the work from going to here is W, let's say. Well, voltage is the work per unit charge. It's the work per unit charge between 2 points in space if you move the charge from one space to another. That's the voltage difference between 2 points in space. So, voltage, volts, it's measured in volts. This is also called potential, also called EMF for electromotive force. Okay. And this is basically a joule per coulomb. So it's work per unit charge. Okay. So actually there's all kinds of ways you can measure a volt or determine the volt. And then you can then define resistance in ohms is, of course, well, it's a joule per coulomb times a coulomb. Right. Oh, well, that's no. Okay. Sorry, it's an ampere. Sorry, it's a volt per ampere. Which is given the name ohm. We've already said that. Okay. So, also volts can be determined by something called the Josephson effect. We won't talk about that now. So, now you have voltage and resistance. So what are some of the things you can do once you have Ohm's law and all these things? Well, you might want to, if you know the whole point of Ohm's law, if you have any two of them, you can determine the other one. Well, let's say you had a voltmeter, and voltmeter is denoted by a circle with a V in it. And you want to measure the voltage across some part of a circuit. Well, you're always making this measurement. There's always some resistance across which you're measuring the voltage. And there's some resistance associated with the rest of the circuit. Well, so whatever voltage you measure, that's the situation you are. There's probably some battery or something back here. But so you can measure the voltage. Now, the problem is all real meters have some internal resistance. So what this is essentially here is something that will divide the voltage. Sorry. What I'm saying is what this does then is you have a situation where whatever current you had going through this resistor here to create the voltage is now split, and some path goes down to here. So it may be the case that the voltage you measure is not exactly what the circuit. In particular, what if you had this circuit? You had and a battery. Well, this is what's called a voltage divider. So the voltage here depends on the voltage here and the ratio of these two resistances. Well, this resistance is in parallel with that resistance, so that makes this resistance a little bit smaller. So that changes the ratio between this resistor, this resistance, and this resistance, so that will change the voltage seen across that resistor. And that's something you can compute from Ohm's law, but we're not going to do that right now. You can do it. Another example, what you can use this for. What if you wanted to measure current? Well, you could measure current with a voltmeter. And if you have a voltmeter across a known resistor and you stick that into an existing circuit, this is R. Well, we now can say the current going through this part of the circuit is V over R. Okay, whatever the voltage you measure divided by the resistance. Now again, in reality, the rest of the circuit has some resistance to it. So in the case of current measuring, these are called current shunts typically. Whatever the resistance you put across here to measure the current, you want this resistance as small as possible so that it won't affect the circuit you're trying to measuring. You can actually figure out what it is because you know what the voltage is, you know what the additional resistance in the circuit. So you can see how that will reduce the current in the circuit based on what you think it is. So the error is you have to introduce a small resistance, which according to Ohm's law will change the voltage slightly. But one of the problems with measuring resistor, let's say you wanted to measure a resistor. Well, one way you could do it is this way. You could have some leads come to the resistor, and you could have a voltmeter that goes across the resistor, and you could also, in series with that, have some sort of current source. Well, let's do it this way. Current source that puts out a known current through the resistor. The problem with this type of arrangement, let's say these are your leads here, there's going to be some resistance in the leads. And you're going to have some current flow through the resistor, these resistors, resulting in a voltage drop. Well, one thing you can do for that is put a second set of leads that have whatever resistance they have through the current deriving circuit. And if this is all right, most of the current will go through this. Almost no current will go through here, although there still has to be some. And this is called a four-terminal resistance measurement, where you have a different set of leads for providing current and a different set of leads for measuring voltage. The whole idea is to cancel out essentially the lead resistance and cause the minimum amount of current to flow through the measurement circuit. Of course, there are other, and you can figure this out with Ohm's law. So basically, Ohm's law is the basis of a lot of electronics instrumentation. Of course, the easiest type of way to make a measurement would be to have a voltage that wasn't there. Another thing you can figure out with Ohm's law, something called a bridge circuit. You have resistors in each arm. And you have some sort of voltmeter here. Oops. Drawing this wrong. And then you have some sort of voltage source here. Okay. If the ratio of these two resistors is the same as the ratio of these two resistors, these are two voltage dividers. This point and that point will be at the same potential, and there will be no voltage here. You could put an unknown resistor here, and then you have two calibrated resistors of some sort. And this is some sort of calibrated variable resistor. You can now measure the unknown by adjusting this until you have a balance condition. In other words, this voltage is zero. This doesn't even have to be calibrated, it just has to work. This voltmeter, for instance, you could just switch the leads on the voltmeter. If the thing doesn't move, or you can figure out how to adjust the voltmeter. If the thing doesn't move when you flip it around, that means the bridge is balanced. because, you know, maybe your zero's off on your voltmeter, but if you flip the leads, it's going to move the needle. So you can adjust this until, or move the indication. If you adjust this until this doesn't move, no matter which way you hook it up, then you can know the bridge is balanced without this even being calibrated. So this setup, you only need to calibrate this ratio. You don't even need the absolute value of these. Calibrating ratios is easier than calibrating absolute values. And you need one calibrated variable resistor. This is the basis of a lot of precision resistance measurements. There are other types of bridges for doing that. This is just one example where what you're trying to do is create a condition where no voltage is between 2 points. Again, something you can figure out from Ohm's law. We'll be back in a minute.
One of LearningMeasure.tv's sponsors is TradePub.com. TradePub.com is a site where one can sign up for a large number of free trade publications. If you'd like to support this podcast, go to the LearningMeasure.tv site, scroll down to the free publications link, and choose one of the magazines or one of the publications or one of the categories and sign up through that link. Each publication subscribed to through this link on LearningMeasure.tv website helps keep Learning Measure TV on the air. Thank you for your support.
Okay. One last thing. What we're going to do is we're probably going to start doing a new thing here. I want to be more interactive, and I want to add a questions part to this, or maybe even a second day for doing questions. So what I want to do is, if you have any questions at all for engineering questions, science questions, measurement questions, any sort of technical question, send me the question at questions@learningmeasure.tv, and we're going to put the questions together, and we're going to read the questions on the air and give some answers. We want to try to do something different. Also, as always, if you want to be on this podcast and you have some sort of test equipment or anything you want to show on this podcast, send us an email at vendors@learningmeasure.tv. And if you have any other suggestions for new features, send us an email at suggestions@learningmeasure.tv. You can actually even send the same sort of things, because the same address works for our .com. So learningmeasure.com, learningmeasure, you can send those three things for the same purpose. Okay, that's it for this week. Next week we don't know. It depends on what kind of email we get. If we don't get any email, we'll again try to do some random topic next time. All right, well, see you later. Bye.